Thank you very much. Hello, everyone. Yeah, and first of all, I would like to thank Pete and Adekunle for organizing this fantastic workshop, and of course to HiRES and to SPICE for this amazing conditions here and for this cultural event we had yesterday night with wine. So HiRES wants to make these workshops to be named as known as the best one. I don't know if it's the case, but it's on the right way, definitely. Peter invited me to present an overview, to have a tutorial on 3D magnonics, which in the easiest case will give us a higher quantity of elements if you're speaking about data processing. So our group study a lot how we can use magnons for processing of data, and also it gives access to new physics, as it has been shown already in many talks. But I took a risk, and I would like to focus also on another slightly different topic, which is inverse design magnonics. And honestly speaking, I'm more in inverse designs than in 3D. But first of all, I couldn't say no to Peter. And second, I believe this, and I did my best to present really good overview. Oh, I hope it's a full overview of what's going on nowadays in 3D magnonics. But I believe these two fields are really need each other. And here demonstrate my skills in operating ChatGPT. Not only Peter is a fan of this. So if you write something like magnon computers that looks like a human brain, you can get such a picture, and it kind of shows us, if to be seriously, where it goes. Because if to speak about inverse design, what we need here, we need large matrices of elements where you can change properties of spin waves or scatter spin waves or something. And of course, the larger the matrix, the more complicated data processing you can do. If it's one plane, it's one story. If it's 3D, then of course it's significantly completely different story. And if to speak about 3D magnonics, we have seen so many fantastic structures and everything. And my message here is that we should not think about 3D structures only as data transport. That we should not only think how to transfer information from one point to another, but we should be able also to process. And that's exactly where inverse design is very good. Therefore, so I hope I will show you some examples how one could think where all this goes. So the field of magnonics, here I would like to advertise Giovanni, who is an editor in PR Applied. And if you will have a dinner with him today, maybe you will get an invitation, like I was lucky to get some time ago. And we have written this nanoscale magnonic networks, which just published on 21st of April. And it was about, so together with Chivan, George Tauber, Roman Verba, and Philip Piro. What's special about this one, we just tried to, it's all about around this one single picture where we show such schematical demonstration how magnonic circuit can look like. Yeah, so you see here are different elements. Of course, it doesn't do any job. It just shows you what kind of elements are already developed in community, and here all these eye catchers within, let's say, last 10 years. So really the database of different data processing elements is very big. Now we need to put them all in. And as you can see, this is 2D in principle circuit. Yeah, so 3D would be a next step. Also, I would like to give an overview on magnonics and this roadmap. So, field is doing very well. For example, you see here Scopus data and versus year, and you see the number of papers where magnon is cited. It now goes as exponential. So principally, field is flying. It's a very good time, and many review papers, perspective papers, and roadmaps are prepared. And we, together with Paul Kabosh and Minzon Kwu, did a job for Maxot Society, and we organized our own roadmap. This one is a bit special. It was a risky, maybe a bit crazy experiment because we did not want to show our vision on community, what's going on. So we didn't want to say, you write this, you write this. We wanted community to give their vision. So it was open, and people were inviting other people. And why it's risky? Because we didn't know where it will converge and if it will converge at all. But principally, it's a bit large, but still quite feasible. And so we have like 61 sections, original sections, so people wanted to contribute. We have a bit more than 100 authors, and I think it gives a nice overview of what's going on. And then our job was to sort all these contributions to sections. And we started with magnonics as a nanoscale, 2D building blocks, 3D building blocks, how to manipulate and amplify spin waves. And then these three last sections are mainly focused on data processing, so which is Boolean data processing, unconventional computing, and quantum business. Also on the right-hand side, you see this scheme, which just eye catcher, which shows you that principally magnet can be used for processing different kind of data processing: digital, neuromorphic, stochastic, reservoir. Quantum magnonics is growing very quickly. You can sense magnetic field, and of course, classically magnets was used always to process RF data. So 5G, 6G is very interesting. It's all mainly still in academic domain, but the potential is here. And today I'm going to present 3D building blocks. And if we go into the, so I also made, before this conference, a quick check. I just checked in Scopus 3D and Magnon. And you see that number of publications is also growing, but also we can clearly see that field is very young. So we have like 15 maybe papers per year. Of course, it's just very rough estimation, but it's obviously just a very good start for the field. And while preparing this presentation, I have found so many cool papers published like last month or last year. So obviously there is signature that it's a very good time for this research. Coming back to the roadmap, who decided to contribute to 3D building blocks? So many of the people you see here, you saw presentation or you will see. Of course, who is not presented is Georg Schmidt, who developed in Halle this fantastic freestanding bridges, which are magnonic and phononic resonators with spatter-Teague. So Dirk Grundler, but his posters, so his students present poster. Alexander Dobrovolsky, Michael Hood has written a 3D part on Fabit, so that's what Amalio presented a lot. Sabri Koraltan, editor Zeus, was mentioned by Laura today. They want to use 3D eyes to guide spin waves along Dirac string. But as Benjamin said, it's not an easy task even to do at the 2D scale. The 3D is even more complicated, but Ricardo Herter is here. He will present the talk. He's a real expert in this business. Sam Ladak presented his work. He's doing a lot of things with Anjan Barman. And here at the bottom, you see Gianluca Gubbiotti, who will give talk. So Florian Cibataro and other people, they are all very much interested in 3D magnonics. So if you will check books, review papers, I would attract your attention to this book of Gianluca Gubbiotti in 2019, where it already was a selection of studies, but field changed strongly since that time. And also I would like to attract your attention to this review paper of Adekunle on flexible magnonics, but as Denis Makarov has shown, this feels flexible in 3D, they are always coming shoulder to shoulder. This is a table of content for the book of Gianluca. I don't want to read here, so maybe only people who are a bit not at this workshop, I would maybe mention Maciej Krawczyk, who is presented 3D magnonic crystal theoretically studied already 15, 20 years ago. And I think like months ago, so there's a publication where it's all realized, there's material, there is also experiment. And I think many of the other results chapters already were presented at this workshop in one or another way. And yes, physicist, of course, first question when I was asked by Peter to do this job, so why 3D magnonics? So what does it give us with respect to 2D? So magnonics, after thinking a bit, I came to three very straightforward arguments. I don't know if you will share this opinion or not. The first one is number or quantity of data processing units. Also, Burkhard Hillebrands is a big fan of it. We discussed this during one lunch. And here I show you another picture from ChatGPT where I actually failed, because what I wanted it to draw one little cube, then one dimensional layer of cubes and 3D cube. And with this one dimensional, after 5 attempts, I didn't manage, so it's still not perfect. But I decided to leave this picture because it clearly explains what I mean. Very simple estimation. We take some data processing units of the size of 10 by 10 by 10 nanometer. It can be part of transistor, for example, or any kind of magnonic unit. Then if you have a chip 1 by 1 millimeter and only one layer, then you will put 10 to the power of 10 units. And if you will do the same, but 1 by 1 and 1 millimeter up, then you will get 10 to the power 15 units. So it means 100,000 times better units. Of course, it opens completely new possibilities, and it's very good way to go. Why it's not done in CMOS nowadays, to best of my knowledge, or at least not to the real three-dimensional? One of the problems is heating, because it's easy to get rid of heat when it's on the surface, but it's very hard to get rid outside, from inside of the system. And in this context, you need a technology which is low energy consumption, which simply doesn't generate so much parasitic heat. And here, in this paper a few years ago about directional coupler, we managed to show also first integrated magnonic circuit in the form of half adder, numerically, but based on experimental components. And we performed benchmarking, and we, so where's my pointer? You can see here that energy which we need, I have a bit problem with this pointer, around 2 attojoules. This is an energy which we spent within magnonic system to do the job. For CMOS, which at that time was future CMOS, now it's nowadays on the market, it would take 35 attojoules. So it means that magnonics can offer 10, 20 times less energy consumption. So it means less energy problems with taking heat away from the circuit. Therefore, I think magnonics is a kind of really interesting way to go in terms of 3D. And the last argument, which is also very clear, is access to new physics. So here I just show you this famous example from Attila Kakai about tubes. So if you magnetize it perpendicular in Damon-Ashbach geometry, you will get, simply due to dipole-dipole interaction, but in such complicated shape, you will get non-reciprocal spin wave propagation. So wave which is running in one direction will have another dispersion, another wavelength, and the wave running into the opposite direction. So 3 arguments. Now let's go through results. In our group, we also contributed a bit to this field. So Alexander Dobrovolsky, who actually just got a call professorship in Braunschweig, so he's leaving our group. He had a project with Dresden Rosendorf and with Michael Huth in Frankfurt, where they studied 3D structures for spintronics and magnonics. And here you also see Sebastian Lam-Camarena, his PhD student, who also did a job. So one of the publications in this direction. So which kind of material, which kind of structures were studied is Fabit. Yeah, so Amalio gave a fantastic presentation. Fabit is a super powerful technique. It can go to whatever you want, 3D nanostructures, very small sizes, different material composition. You can tune chemical composition. So here it was used cobalt iron, which, as has been shown by Hans Nembach, Justin Shaw, can offer a very good small spin wave damping. And what kind of structure was studied? It was a Vulcano, it's named, which you can, the easiest way to understand what is Vulcano is a disk, a magnetic disk on top of which is placed a ring. And what has been found here is that, of course, modes in disk and in rings were known before. But when you place one on top of another, you see here there's the magnetization field. Its place changes landscape of magnetization, magnetic field inside of the structure. And you clearly see that then kind of it decreases effective width of the diameter of the disk. So modes are changed. And you can see all these modes which were very carefully analyzed experimentally, drum modes, radial modes, and here on this side. And that's more or less how, what kind of new physics is coming from the 3rd dimension in this case. Everything was simulated also numerically with CHUMAK, good agreement, so physics is well understood here. Second paper is recently published. Also, it's a Fabit structure, but here we see just one plane waveguide, 2 antenna, one to excite spin wave, another to detect spin wave. If spin wave can propagate such a long distance, and brilliant light scattering spectroscopy microfocused was used in order to detect spin wave. And one structure, as you see in this profile, is just rectangular waveguide, so just standard strip line. Another one is has a curvature. Yeah, so it's like such a half tube with such 2 shoulders, again produced in the group of Michael Huth in Frankfurt. And they performed systematic studies of thermal measurements and then also excited measurements. And you see that's how spectrum looks like in a waveguide, and that's how it looks like in the curvature. And you see obviously the third dimension, simply that there is a more complicated shape, bring big changes to the dispersion of spin wave properties. But this paper also brings us to a bit less positive conclusion, because this spectrum was measured actually under antenna, where this triangle is. So it has been shown that it's really hard to get a propagating spin waves, long-range propagating spin waves, because of material. And here it brings us, so I will be given such challenges. I think it's very important for the healthy growth of the field also to face challenges openly. These are challenges not actually mine. This is what Amalio has formulated in the very first talk. Quality of 3D nanomagnets is very important. And Fabit has also drawn back that it's very complicated technique, that we have a limited choice of selection, of choice of materials. On another hand side, of course, you can tune, for example, cobalt iron. Alexander has shown that you can change magnetization. It gives a lot of power, But I was really honored to be an opponent of PhD student of Amalio, Lucas Koric. And there was this fun format when we had a dialogue for 2-3 hours. And a lot of time we devoted how to take carbon out of the structures. So I'm not expert, Amalio can say more, but as far as I understood, there are many ways how one can improve significantly the structures. But at the same time, I think there is no way to get a perfect single crystal structure with Fabit at this stage. And maybe for magnonics, in some cases, you can work with any material. For other cases, you really would prefer to have something very idealistic, like, I don't know, LPE, Trimaran garnet, or something like this. Good. Another results was in this direction were obtained by Nura Senbam, my PhD student. And what she is doing, she's trying to follow up this research on directional coupler, which we made with CHUMAK some time ago. So what is directional coupler? It's if you have two magnonic waveguides, here's one, here's another. You have antenna spin wave source to excite spin wave here, it comes here, and then dipole-dipolar coupling couples these two waveguides, and spin wave energy can jump back and forth. And afterwards, you just increase spacing so that they don't talk each other. Here, just two outputs. And we have shown that depending on frequency, on coupling, you can have a jump of the spin wave and power and energy to other waveguide. You can split 50-50. You can jump it back. We also have shown nonlinear functionality. And at the end of the day, we've shown how one can get some half-adder, yes, a more complicated data processing unit. What Nura is doing, she's focused on non-reciprocal magnonic directional coupler. Again, we are not pioneers here, so Mathieu Bayol, so John Deep here is in this room. And we have shown it, Maciej Krawczyk studied, Philip Piro. If you take a YIG and put on top another magnetic material with another MS, for example, cobalt iron boron in our case, then dispersion is getting very asymmetric. And then you have properties of wave running in one direction are very much different to the properties of running in the opposite direction. And if you have two waveguides here, then what happens, you will get splitting of this dispersion. And the strength, how they couple these two waveguides, is actually given by this delta K. And you see this delta K is smaller here and bigger here. So it means the distance which propagates spin wave before it pumps energy from one waveguide to another will be different for these different waveguides. And then you can have such situation. So you see that here it's given less often, and here's jumping back and forth more often. And then you can get such a directional coupler where signal from port 1 goes to port 3. From port 3, it goes not to port 1, as it would be normal directional coupler, but to the port 2. This is very good, for example, for smartphones. You have here source, strong power, this is antenna, but when you receive very weak power, of course, you want to separate them, and signal from this one goes to sensitive source, a detector on the port 2, like bi-circulator. So what has been done, so structure was studied, so we tried EEC 100 nanometer COFAB 40, Also with silicon oxide, 5 nanometer spacing in between because CoFAP increases damping, and damping is an issue. Silicon oxide helps partially to get rid of this problem. And then it's numerical simulations, and also it's key result measurements measured together with the team of Philip Piro and Kaiserslautern. And you see here that this is K0, yeah? So dispersion is very asymmetric. So there is a region of frequencies where spin wave can principally run only in y direction or have at least K. So it's good for a diode effect or something. So this concept works. Structure was fabricated and currently under the measurements. What was tricky here, this structure to make it was hard. So what is here is stock of all this is around 150 nanometer. Width of waveguide 150 nanometer, and you need spacing 150 nanometer that they coupled. Otherwise, if it's larger, it's already coupled and it's not strong enough. And it was really a complicated task, but Nura is very persistent. She managed. Structures were done in SciTech in Brno, where Michal Urbanek is taking care of the instrument, and we also do all physics together. So she managed to do it, but it was very complicated. And of course, much better way would be to go to third dimension. Yeah, so if you would put waveguides like it's shown here, then you control spacing just with the thickness of your layer. You can go from 1 nanometer up, you can increase the coupling, everything would be different. Therefore, it's a nice example why 3D, third dimension, would be really nice here. Okay, now let me go what's going on in the field. So first I would like to refer to this paper of Dirk Grundler, 2023. And what he did using two-photon lithography, and then, as he quoted, this resist with nickel shell using plans that enhance atomic laser deposition. And this study also was presented yesterday on poster. And afterwards, they measured using brilliant light scattering a thermal spectrum of spin waves. And principally, very big structure, very nice result. Spectrum can give already a lot of information about modes, magnonic modes within the structure. But it also brings us to challenges. And one challenge is spin wave excitation and detection. Yeah? So in ideal case, we don't want to see thermal modes or to excite them everywhere. We want to have here source of spin wave and there, for example, detector. We want to have magnon transport from one point to another. And this is a big step forward, but not yet the final realization. So this is a paper which I just mentioned at the beginning. So it's Kaiserslautern, also Maciej Krawczyk did simulations. So Justin Lando made the structures in Japan. And what they did, they used this, I'm not a material scientist, but they say that I should say block copolymer. And so it's self-assembled polymer where you can get a really big structure, and then you fill with nickel, 50 nanometer period, and size of node here, 4 nanometers. So it's really true 3D and very big, and you can choose different materials. So I think this is very interesting technique. Again, there was a poster yesterday where numerical simulations were presented. Of course, depending how you magnetize it, you will have different spin wave modes in different directions. But they also performed thermognetic resonance studies and compared experiment and theory. So there are some peculiarities, but principally, we can say that there is already a study of such structure going on, and also very recent publication. And this is maybe the first true such high-impact publications of Sam Ladakh and Jan Barman, 2021, in the direction of 3D magnonics, 3D artificial eyes. Yeah, so we have heard today a nice talk from Laura Heidelman about 3D eyes. Of course, it's very interesting for spin waves as well. And what was done here, again, two-photon lithography, thermal evaporation, 50 nanometer thick permalloy, but they could have only 4 layers because of shading effects. Yeah? So that's also a limiting factor which we need to take into account. And they measured here BLS, but of coherent magnon. So it was placed on FMR3, probably excited. It's not thermal like Dirk did, but it's excited by microwave field magnons.
I have a question on your previous slide, if I may.
Yes?
So I was thinking, it's a naive question because I'm not in the field. So here you have a massively 3D structure.
Yes.
Okay, so in 3D you have long-range dipole fields. So could you
Yes, I think this is a very good point. Of course, there will be non-homogeneous broadening, but there will be many other issues, maybe even more important. So first of all, is internal magnetic field. It's strongly non-uniform, and when you apply bias in field inside will be very different at different sides.
Sorry, this was my question.
Ah, this one. Yeah, because on top there will be something else. But yes, this is the issue, and I discussed yesterday next to poster about comparison, experiment, and theory. If I understood it right, you can study all this influence of internal field and so on numerically, but it's hard to compare to experimentally, because in experiment, if I got it right, there are clusters. So they are not all oriented the same. There is part of sample with this orientation, this and this. And then when in experiment you measure, all these modes are broader. You measure a macroscopic signal. So it's not the most trivial task. Yeah. Good. Next, so it brings us to the following challenges. So we need to keep in mind shadowing effect, and we need to search for localized spin wave sources, and we need 3D spin wave detection. And here, as Claire has explained, again, published 9th of April, I don't know, it's a very special conference. This, I think, is a breakthrough for our field, for magnonics, because they reported on 3D detection, 3D mapping of spin waves in synthetic antiferromagnets. So it's permalloy, cobalt, iron, boron. It's not, it's quasi 3D structure, but technique itself, which is time-resolved magnetic laminography. So they really show that they can map spin waves in all the structures. Of course, then the next step would be to take this very complex 3D structure to excite it locally and to see how spin wave propagates. So I think it's a very powerful tool and very great news for the field of magnonics that this technique is established. Now I'm coming to the second half. I will try to present you what's going on in the inverse design magnonics. Why inverse design? Because principally it can be used for any type of computing, starting from binary data, neuromorphic, stochastic, reservoir. Okay, stochastic, it's not really the same, it's a bit different. But let me show what's going on. So here, more people involved in the study. First of all, CHUMAK, who was postdoc in our group, now he's prof in Wuhan, established his own group, and Andrii Warren, a PhD student following it, is trying to realize this inverse design structures experimentally, and develops also under the co-supervision of Klaus Abert from the group of Dieter Süss, new numerical approaches to be able to simulate very complicated structures. And on experimental realizations, again, Nura and Fabian Maichi helps her as a master student. And so they are pushing another direction, which I will show you at the very end. What is inverse design? How usually it works? Usually we have some input information, we have some geometry design, and we don't know what will be as outcome. We just perform measurements and we know what we have. Then what we think, just change geometry until we get what we need. And this is a direct design. Inverse design is different. We don't know what is designed, but we do know what we want to achieve. And we know what is the input signal. So we go from input and from output in order to get design. And pretty often we also don't know what is that. Computer is giving us this design. And that's a very nice approach. We took personally this jumped on this field because of motivated by optics. So inverse design photonics is already a bit more established. And we wanted just to compare if it works also for magnets or not. And here is our first demonstrator. So it's 2021 already, but I still will explain in a few words how it works. So this is a demultiplexer. It has one input, two output, 1, 2. And we send two frequencies in linear regimes. They do not interact, and we want to have F1 here and F2 here. The region, however, spin wave where actually inverse design is here. We just take this one by 1 micron region, split it into 10 by 10 cells, 100 by 100 nanometer each. And what we do, we just remove randomly yttrium iron garnet from this some of the cells, voids, make such voids, and then we simulate simply how much energy goes at frequency F1 to one channel, how much F2 goes here, F1, F2 here, and then we define so-called objective function. So it's just a measure how good functionality. We more or less convert what we need into mathematical language. So the larger F1 here, the larger objective function, the larger F2 here, the larger will be, and so on. And afterwards, we just do a So we measure, so we perform simulations, and then we can define, just get one scalar variable, just objective function. Afterwards, the procedure is very simple. It's named direct binary search. We randomly take another cell. If it was YIG, we replace it with air. If it was air, we replace it with YIG, and we simulate again. Again, F1, F2 here, F1, F2 here, calculate objective function. If it's better, we leave this state. If it became worse, we just ask computer to take to the previous state and jump to another random value. And then one iteration means that we checked all of these elements, and you see that objection function can be strongly improved, and then we have a few more iterations which just slightly polish the structure. And at the end of this process, we have completely different distribution of weights here, and that's spin wave how it looks like. So really F1 at 2.6 gigahertz goes to output 1, 2.8 gigahertz goes to output 2, works very good. This is the same way you can do multiplexer to mix two frequencies. Then, here's animation where you can see how it propagates, but the idea is very clear. And since it's numerics, it's always good to show some animation. And of course, for us, very important nonlinearity. So Giovanni, I didn't count, but I think he said the word nonlinearity maybe 5-10 times in his yesterday's talk. We also understood that you cannot process data without nonlinearity. You need, in the simplest case, you can need a switch that's small power. So this is field of excitation, which we apply here to excite the spin waves. Small power energy should go, spin wave should go to one arm, and high power should go to another. It's one of the examples, yeah? And with this, you can do binary logic. With this, you can do neuromorphic and many other stuff. So only what we had to change, nonlinearity needs a bit of time and space to accumulate. We increase the size of this element twice, that it works good. But in the rest, we changed only objective function. So the same frequency, just power is different, and we just ask computer the same routine, all the same, and it works. Afterwards, we thought, okay, nonlinearity is fantastic. It's a key to the data processing. But what else is special about spin waves compared to optics? Of course, non-reciprocity. Spin waves are non-reciprocal. And then without much thinking, we just defined objective function in a way that signal of the same frequency, the same power, goes from port 1 to port 2, from 2 to 3, from 3 to 1, just by circulator. And it works. And then we started to think, and it was magnetized out of plane. We worked with so-called forward volume spin waves, which are known to be not only reciprocal, but also isotropic. So principally, we have realized that it should not work. Then we started to go back, went to nanowave guys to try to understand. And physics, for people who are deeper in magnonics, is that since structure is so small, width of structure is getting comparable to thickness. And if you magnetize like this, just look from the side, and you will see that this is like Damon-Eschbach. And it has this, again, dipole-dipolar field contribution, which makes, gives us very weak, actually, non-reciprocity, but computer is able to summarize it and to put it into some very macroscopic outcome. So it's a very nice example that computer pushed us in also in terms of physics. Compared to optics, what is good, bad? Good principle is that it's scalability. Just to show that we can make everything 10 times smaller, so with 100 by 100 nanometer, everything works, slightly higher frequency, less simulation time, just better. So for magnonics, the smaller the better. That's a very good thing. Pronounced nonlinearity, you cannot achieve it in optics, and natural non-reciprocity also in optics, it's not so easy to get. So inverse design works. What's going on in the field? It was a very interesting story, because we have met with Georgi Xaba. He organized a workshop in Budapest. We have realized, like a few years before this, where it goes, and it's all nice. And then we kind of lost contact. And at some point, we have realized we got in contact that we both are preparing paper and ready to submit that. And then we were thinking what to do, and we decided a very clear plan. We put it on archive the same day. We submit to the same journal the same day with cross-references to archive. And then it worked out very well. They had a bit more nasty referees, so it was published slightly later. But these two papers, which are done in parallel, and this is also very important. They also use inverse design, with the difference that they don't make holes in the X, they put nanomagnets, which can be magnetized up and down. And they have one big antenna and 3 outputs. And then they play with this magnetization in order to get any kind of any kind of functionality. And they went immediately to neural tasks. So they defined this recognition between vowels, E, and what they did, they just took a real audio profile of this vowels, compressed it, of course, to gigahertz range where you can excite spin waves, and then you excite it when it's one amplitude modulation second or third. There were changes as magnets until one profile goes always to this output, another time amplitude modulation goes to this one, and third one to this one. Principally, it works. They have shown also that nonlinearity matters, and all this shows us that principally this kind of neuromorphic network is easy and very good, actually, to be constructed using magnons. What is the problem here is problems that if we want to go to even more complicated tasks, we have troubles even not with power, but with memory of computing. So it means that for inverse design, you need to save all these results of simulations all the time, and pretty quickly, even if you have supercomputer, you're out of memory. And so there are different ways to do, but there is one adjoint method which Andrii with class developed, and he will present at Bologna on ICM first results. So there is a way to overcome this issue, but you need to simulate slightly different approach. Yeah, and what I forgot to mention, why inverse design, why I like it so much, this is what CHUMAK did, directional coupler. It took him 2-3 years, or us 2-3 years to do it. And for inverse design, all this completely 3 different functionality, it was 2-3 months, all was simulated. So it's a really powerful device in terms of. This paper is very important, the same team of people, George, Adam, Wolfgang, but the work was done by Martina Kischle to München, and under the supervision of Markus Becher. This is the first experimental realization of inverse design. And what they did a spin wave lens. How they achieve it? They again use YIG, but they do ion implantation using gallium FIB simply. Then they checked how much they change MS when they implant, change dose for gallium. And then they knew what they want. They want to have such a lens that one antenna excites plane wave here, and they wanted to find such profiles that it all comes here. They developed a spin torch code, which is open access. You can use it for yourself if you want, and use a spin torch to get such profile of magnetization, which you need to do if you want to focus a beam. And this is profile. This is what they wanted to achieve, and this is experiment obtained with magneto-optical Kerr effect, time result, and principally works good. So it's a very important work. And but here it brings us to 2 negative things, is that first of all, you need ideal match between experiments. So if you need to change here magnetization 10%, simulations tells you you should really achieve 10% in experiment. And that's not so easy, especially with ion implantation. And second, still you need to simulate a lot in order to get that profile. And this brings me to the last result, which I would like to present here. It's a result of Neuron, where we did purely experimental inverse design, so without any micromagnetics. So it kind of, some people name it like hardware for inverse design. So we name it inverse design processor because optical people, they recently published something related. But idea is the following. We don't want to do any simulation. We want to do it directly in experiment. So we went back in sizes. We went back to classical magnonics, where we use 18 micron thick YIG and size of the structure 1 by 1 millimeter. So we do not pretend here on application assumption, energy consumption sizes. It's not about modern science, but to understand if it works, if it's possible, to understand if nonlinearity matters, which algorithm is better to optimize. This is just perfect sandbox. And what we did on this YIG, we developed such a complex PCB where we have matrix 7 by 7, such omega shape loops through which you can send current up to from minus 1 ampere to 1 ampere. So we locally change field them, and we have really 49 current sources which independently control all these guys. So we can create any profile of magnetic field we want. Then we added 3 antennas to input to excite to detect spin waves. Why 3? Just to have some freedom, because potentially this thing can do neuromorphic binary data processing, so we just wanted to do whatever, to have freedom for any kind of data processing. But at the moment, we used only 1.1 and 1.2 antenna, what I will present you. We started with the first. Then how it works, the same idea. If you understood inverse design, it's no problem. So you can easily check it. You connect it simply to vector network analyzer. You excite spin wave. It propagates through all this gradient. You detect it. We switch, you decide on which antenna you detect it. You send your transmission to computer. You define the objective function, what you want to obtain. Computer simulates all these checks, and then uses any kind of algorithm to change this field. And you measure again. And one run takes, I don't know, some second or so. So instead of 1 hour in numerics or whatever, or many minutes in numerics, and it's all done directly in experiment. It was not easy, so this is a photo which I took just when we made the first run. So you see this actual device is staying here, but these are just power supplies to control here, Nura, Fabian, and class. They keep people, and actually at that night it didn't work. But we know that if you choose very complicated algorithm, it's very good to put your computer down in the middle of night. And but we now have tested different algorithms, and it works quite good. You will see spectrum, transmission spectrum of spin waves. It looks with such notches. This is technical detail, and here with Kalinikov's-Slavin model, we simulated. The point is that there are many the thickness modes, and there is anti-crossing here. So these notches are not very nice, but they don't play any role on that's what I explained to you. Message here is just that we understand what's going on here. There are no surprises. And then which functionality? We started just with simple notch filter. One antenna, one antenna. We have some transmission, this dashed line. And then we define some region like 5 megahertz wide. And we want to have here suppression. That spin wave outside of this region propagates as it should, but here it goes as down as possible. So we define some objective function in this way. Algorithm, you can try different algorithms. It's really cool. So we tried binary search, like similar to the direct search like it was before, when you just change one of them and see what works better. Here it was so-called generic algorithm. It's already more complicated AI driven, one can say, algorithm. And it's somehow similar to biology. So it makes some tests of different random distributions and selects the best, make parents out of that, introduce some mutations, and then you can get better and better result. So here you see the map of this 49 currents. So blue means minus 300 milliamp. We just limited here. Red means up, and that's how computer was optimized in sync. Can I show this animation? Oh, animation doesn't want to show. Well, let me check once more. Yeah, so that's what you measure. It's not every configuration, it's just every some 100 or so. But at some point, it will make this notch, and you see it's minus 90 dB versus minus 30 dB. So it's 60 dB. In reality, it's 50 dB. It's 4, 5 orders, 6 orders of magnitude increase in rejection. So even if it doesn't look so cool, that's because of logarithmic scale. In reality, 10,000 times of a rejection is achieved easily. Then we wanted to be sure that it really works for all frequencies, not for some given, maybe we have resonance between omegas or something. So we carefully checked all frequencies in big range for wavelengths from 110 to 70 micrometer. Works good for everything. So it's really true design, a true inverse design. We wanted to know how it scales with the lateral sizes of our omega. So it's COMSOL simulation of the field created by this omega, characteristic size 0.5 millimeter. Then we went to wavelengths up to 1.2 millimeter. That's the advantage of spin waves. That's what they cannot do in optics. We can go to any wavelengths from Angstrom till up to centimeters. And we see that it still works for this 1.2, but suppression instead of 10,000 only 200 times, so it's already bad. So it means that we cannot overcome the fraction limit. So we still have to wavelength should be smaller than size of our structure. And then the last what we tested, of course, the multiplexer. As I said, it should work for anything. We just defined objective function in a way that frequency 1 goes to one antenna, frequency 2 goes to another antenna. And then again, just some algorithm. It took a bit longer, but it still found such a configuration where maybe I can show on this curve. You see that here red has minus 90 dB, blue has original minus 30, and in another channel, blue has minus 80, and red is minus 40, so more or less close to the original. So demultiplexer also works, or you can see it like this, formation of bands. It's not very well visible, but this blue line is our notch filter, the multiplexer, which we need. And you see, and this is iteration. You see that after some iteration, it really starts to form band gap here and here, like it's shown. Good, so that's actually the end of my talk. Before I finalize, just I want to use opportunity to make advertisements that Alexander got professorship, so it means that senior scientist position in our group will be opened again. So we are searching for experimental scientist in magnonics. It's tenured position, or you can use it if you are young, ambitious for 5 years for habilitation, and then can apply for professorship. So if you know somebody or you are interested, please write me an email. I would appreciate this a lot. And I'm coming to the conclusions. So I hope I could show you that 3D magnonics has potential for data processing. So at the moment, we have already many structures. There's still a long path to improve them, but we have also technique to detect this spin waves in 3D. So it's a really great path. I hope I also could show you that it makes sense to merge, but of course we would need reconfigurable structures here. Yeah, to do 3D reconfigurable with inverse design, then I think we will get very high power in terms of data processing. Don't know if it will be as powerful as our brain, but definitely it will be much more powerful than anything reported so far. Of course, there is a list of challenges which we have to address. So choice of material, quality of material. We need to find a way how to excite spin wave locally, how to detect locally or 3D, as we heard here at this workshop. A limited computational power, memory. So we always rely on numerics here in this case. So also we need to think about novel approaches. So a lot of things to do, but also very clear understanding where to go. And with this, I would like to thank you for your attention.